today we will continue to discuss the design of some parameters for the bearing test. So last time we talked about the using the power ratio K to classify what is the low speed bearing, what is the high speed bearing. Okay. So we have some conclusion to that. So we are using the power ratio, which is the friction power divided by the pumping power. So we using the K constant to classify. If K is greater than 1, it's called the high speed bearing. If K is smaller than 1, it's called the low speed bearing. Okay. So we have addition 1. So okay, ranging from 0 to 1 is called the low speed or moderate speed hydrostatic bearing. I would say most of the hydrostatic bearings apply in the industry or apply in machinery. It's falling into this category. So I would say maybe 90% the hydrostatic bearing in the machine tool application. So in the low speed bearing category. We also have an equation to estimate or to calculate this temperature rise if we don't have any cooling system for hydrostatic bearing. We can estimate the worst case temperature rise for lubricant using this formula. Okay, so under the assumption of the most of the, I would say, 100% of the heat will go to the lubricant. Okay, we consider only the convection case. We neglect the radiation and conduction case for the heat. And then we discuss some of the design parameters for our hydrostatic bearing. For instance, language ratio. Okay, so the language ratio is important design parameters for the hydrostatic bearing. So we have already some research results prove the optimum or the best language ratio for hydrostatic bearing is equal to the 0.25. So this is A stands for the length and L is the bearing width. Okay, so the ratio is equal to the 0.25. For most other cases, I mean, if you don't have any other problem, you always use this parameter for your design. Okay? Um, this is a good design parameter for the hydrostatic bearing and aerostatic bearing. Okay? So in this case, this is the, the arrow is the diameter of the bearing head. So, and for the German bearing, this is the length width. Okay, this is the total length for the design. And last time we also discussed about the viscosity. Usually, viscosity will affect your heat generation, especially during high speed. Okay, if you have a stiff viscosity, which means the viscosity number is big, then you will have a lot of heat generated by the viscous friction during the motion. Okay? So for high-speed bearing, you tend to use low viscosity lubricant for the hydrostatic bearing. But usually it's not for the design, okay? Because as I said last time, we have a different viscosity for the lubricant. For the ISO standard, this is the standard product for the petrol company or the oil company. They will provide the viscosity grade with the number 2, 5, 10, 15, 32, 46, and 64, 68. So we cannot choose the viscosity other than this number. Okay, so it's not always you can find an optimal viscosity. And usually we take a reference from the commercial product. from the market. Okay. The main concern is rotational speed and varying pad area. Okay. That will decide that will decide your viscosity number for your application. 所以我们选的那个粘度是可以随便挑的，因为那个油品公司或石油公司，他们出产的粘度是有一定的粘度等级，不是说你想要几号就几号。一般来讲，就是我们选这个的话，主要考量就是你的转速跟你的气压轴承的油腔面积，面积越大，它其实产生的那个摩擦热就越大，所以粘度就是不可以选太高。So viscosity in this case, okay. So if you have a isostatic bearing rotate in very high speed, you need to select a small number of viscosity grade. If your moving speed is very low, you have a uh, heavy loading for your bearing, then you tend to select a thick viscosity lubricant. Okay. So usually we will not do the same process like this to find the optimal viscosity by series. Usually we select according to the reference from the market, you select the viscosity like the similar product. Okay, then you use that viscosity number do some estimation or calculation in your formula and see if the friction power, so like previous one, so you can using that viscosity to calculate the friction power and see if the friction power is too big or appropriate. So most of the place, this one is also is you select beforehand. Okay? Just not analyze like this also. And also for the theoretical analysis, you can analyze optimum clearance for minimum power. Okay? But for the minimum clearance, it's not decided by the designer of the hydrostatic bearing. This was constrained or decided by the manufacturer capability from your hydrostatic bearing manufacturer. 另外一个上一次讨论的也是这个间隙的部分，虽然理论上可以去分析最佳的间隙，但是间隙的话，基本上我们其实不会去做这个分析哦。大概你可以做这个分析的话，大概只是做个参考，因为你可能要从厂商那边知道他们的组装功能最小能够组装的最小间隙是多少。那再来的话就是我们，当然你也可以用这个方式，因为我们都是用最小功率的那个限制条件去做设计，所以我们其实可以去找到一个最佳的间隙，但是这个间隙值通常也不一定是适合。So this clearance is also not always appropriate to use the right from theoretical analysis to find the optimum clearance. So the minimum clearance was constrained by the manufacturing worker, the capability for the assembly. Another constraint is that if you have a higher clearance, a bigger clearance edge, then you will have a lower stiffness. 间隙其实是不能随便决定，这是油墨间隙。油墨间隙的话，它会影响到你的刚性，所以这个我们后面也会去讨论到。当你其实你，比方说你的风筝的性能，其实你也可以改变不同的参数，都可以影响风筝的性能。但是有些我们会固定不动，去改一些比较关键的。And later on we will discuss on how can we manipulate or change the bearing parameters to get a better performance. And some of the design parameters, like this clearance, or like the previous one discussed, you should select very carefully because that will affect your bearing performance, especially for the clearance. This will affect your stiffness of the bearing, especially when your hydrostatic bearing is used in the machine tool, especially for the cutting machine tool. 当你是用在切削工具机的静压轴承的话，你的刚性就会影响你的切削，所以 so we can find out the optimum clearance edge by using this equation. The total the the total power, the right equal to zero, we can find the optimum clearance for the minimum power computation. Okay. Yeah. For the optimum power for the high-speed bearing, this was when you are designing high-speed hydrostatic bearing, probably you will use this optimum power ratio. So, and then there are some general rules when you design the hydrostatic bearing. So, here is the first one. In order to reduce the temperature rise, it's better to reduce the bearing, the length of the bearing rather than increase the clearance. Because if you reduce the length, you can reduce the bearing head area. So the friction power will decrease. Therefore, the temperature rise will also decrease. Okay. Another case is that if you increase the bearing depth or bearing clearance, you can also increase or you can reduce the friction power. So in that case, you can also reduce the temperature rise. But the strategy is that first you need to reduce the language, okay, rather than increase the clearance. Because if you increase the clearance increase, the thickness of the barrier will decrease. Okay? So therefore, you should select the first strategy, just reduce the language ratio, and reduce the language. 所以像这个，如果我们的轴承的温度太高，我们可以降低那个风油边的宽度，也可以增加油膜间隙，但是我们这两种都可以让油膜的温升降低。但是如果你增加它的油膜间隙的话，轴承整体的刚性，不光是温度会下降，你的刚性会下降。刚性的话，在切削路径技术非常重要。Course in some trade-off. If you reduce the liquid, then your volume flow rate will increase. So if you reduce the liquid, which means that the volume flow rate will increase. 你把那个风油边的宽度降低，你的油就非常容易流出去，所以你的流量会很强。所以我们一般来讲就是，你必须做一些折中，你要能增加，应该降低温升的话，你变成就是你用流量增大来交换。The second rule or second rule of thumb is that if you decrease your viscosity, there are two effects. Okay, viscosity shear will reduce. Okay, and also the bearing stiffness will reduce as well. Okay? And then if you have a smaller viscosity, temperature rise will reduce. 所以你如果降低粘度的话，那个刚性会降低，收成的刚性。你用比较黏的油，收成的支撑力比较好；你用比较稀的油，收成的支撑力比较差。但是你降低粘度的话，当然就是粘度越低的话，流体越容易流动，越不容易产生分散。但是它的刚性会降低，就是你轴承的刚性，承载力也会降低。So the low carrying capacity of the hydrostatic bearing will also decrease if you decrease the viscosity. Okay. So the most critical bearing parameter for hydrostatic bearing is clearance bearing depth. So when you want to change it, you should think very carefully. So 这个最关键的那个设计参数就是我们的油墨间隙，就是我们刚刚讲的间隙或者是油墨厚度。当然，我们也有一些we have some constraint for that. Last time we mentioned for this. So the minimum gap should be greater than 10 times of average surface roughness. Okay, 10 times. 这是它的最小的。但是我们讲过，这最小的间隙值通常是决定组装功能的技术能力决定的最小间隙，不是我们想要多小的东西。But in practical, usually the minimum bearing gap or bearing clearance is decided by the assembly workers' capability. You can also take a reference from the commercial product in the market when you design a bearing. Okay? Because usually you are not the first person to design this kind of hydrostatic bearing product in the market. So you always can take reference from the commercial product. 所以大部分来讲，其实你这些参数的话，也可以参考就是市场上面的一些商品的参数，但是有时候商品不一定会把所有的参数都标示出来，大概是这样。 So, and then we have the optimum pressure ratio. Uh, Usually for the no matter low speed bearing or high speed bearing, we always select the optimum pressure ratio equal to 0.5. Okay. This beta value equal to 0.5 means recent pressure is half of the supply pressure. Okay. This is all, I mean, this is the same as the rule of thumb. If you want to design, usually you will design like this. The recent pressure is half of the supply pressure. Okay.所以这个是我们也是常常这样学。就是我的油箱的压力大概会等于我公压的一半，所以这个其实是在小孔节流器的话，这个是最佳的节流，就是 optimum 的最佳的压力。This is the optimum pressure ratio for the Olympus restrictor. Although for the capillary restrictor, it's a bit different from this 0.5 level. But most of the cases we design our hydrostatic bearing using this pressure ratio 0.5. 所以我们大部分设计上还是会用这个1.5，就是我的油箱压力大概是我的供应压力的一半。For the capillary restrictor, the optimum pressure ratio is equal to 0.7, not really 0.5. Okay. It's a slight difference. 所以这个是小孔节流器的最佳的压力是0.5，所以就说我们的油箱压力一般来讲，大概是我供压的一半。So for bearing test capacity equal to the recess pressure multiplied by the equivalent bearing pad area. So PR multiplied by. So once we know the bearing pad area, we know the load capacity. For example, for our dry cable in milling machine or in lathe machine, then we know the recess pressure. So once we know the recess pressure, we know the P because beta is equal to PR divided by PS equal to 0.5。所以我们从负载切削率那边可以算出总的承载力大小。油箱的面积我大概可以估算，我就知道大约要多少的油箱压力来乘上我的那个加的面积，才可以支撑我的切削率，或者是我的外部。像我知道 P R 的话，我用这个贝塔的0.5就知道供油压力的 PS。So this is the way you can estimate the PS because usually we using the pressure ratio equal 0.5 to design a hydrostatic bearing. the method restrict is Olympic or temporary. We have another example, which so here is the speed parameters. Okay. The use of a speed parameter here is optional. And the optimal design can be achieved by simply using the friction power equal to the pumping power. In this case, we can obtain the optimum speed parameter, SHO. This was derived by the author in 1969. So, most of the theoretical studies of hydrostatic were completed during 1990s or 1970s. So, the first design textbook for hydrostatic bearing was started from 1983。其实大部分的理论部分大概在60年代跟70年代，大概就通通都会推导出来。所以第一本的一些那种的教科书大概1983年出的。还有就是 also in the design of hydrostatic bearings, we can distinguish the design parameter or design variable by classifying them into the two different variables. One is the duty variable, the other one is the right variable. Okay. So this you might see in some textbook. What is the duty variable? Duty variable related to the various duty requirements, such as the speed, size, supply pressure, viscosity, and clearance. So this kind of design parameter or design variable called duty variable. And then we have the right variable. The right variable was obtained from the optimal performance and bearing shear consideration. So in this case, the bandwidth ratio, pressure ratio, power ratio, and friction area factor are fully into this the right variable, into the category of the right variable. So this is just a terminology for the bearing parameters or bearing variables. the power ratio between 1 and 3, then we can have the formula is in page 58. I think last time we already uh, explained the diagram figure 3.1. So in the 70s and 80s, the computer capability is not so good. So therefore, the design of the hydrostatic bearing are using the design chart like this one. 在70年代、80年代，电脑的运算能力没那么好，所以他们的设计通常都是用这种图解法去做设计。So this is the design chart draw using the constant k equal to 1, beta equal to 0.5. So we have a circular bearing pattern, rectangular bearing pattern, and square bearing pattern. Okay. So in the horizontal is the language ratio. 0.25 is the optimum. So it started from the 0. And then so the vertical one is the speed parameter, optimum speed parameter. Is actual. So we have a different meaning from this drawing. I think so in this case, square bearing pattern, the length and width ratio equal to 1. For the rectangular one, the bearing width divided by the length equal to 10. And for the design, it's not so difficult. Okay. Just pick the bearing pattern, what type of the bearing pattern you are going to design, and you select the speed parameter, and then you decide the language ratio. Then that's all. You can have all your design parameters from the chart. But of course, if your width divided by length ratio is different from this chart, you need to find out different chart for your design. 所以这边的话就是看你的场观比是多少。像这个是正方形的油枪，这个是矩形的油枪，是1:1。设计的话其实不是太困难，看你的 操作的轴承要运转的速度是多少，决定你的速度参数之后，大概你就可以去决定你的轴承的公有边跟它的宽度。所以设计上基本上就是直接用这张表就可以决定，所以基本上不需要任何专业啊，就是你只要拿这张表来看你要设计的就可以。We take a break. Okay. For journal bearing, you can also use the design chart like this. It's a similar one. So this is the journal bearing, and this is the recessed journal bearing. This is the non-recessed. We call it plain journal bearing. 是有油枪跟没有油枪的，这个是有油枪的。So it's similar. The horizontal is the leg width ratio. The vertical one is the speed parameter, optimum speed parameter. Of course, this charge is valid for the power ratio equal to 1, the pressure ratio equal to 0.5. So here we have two examples in the textbook, page 61 and 62. You have example 3.2 and 3.3. And now from the page 62, we want to look at how the temperature rise will affect the bearing. Okay. The first one is the zero speed bearing. We have a table on that. So, was wrong. So this one is viscosity, and this is the clearance. So in the language ratio, here is the thickness. Thickness of the barrier. This is the pumping power, friction power, total power. So total power equal to the pumping power plus the friction power. You can see the difference. Okay. So the design one and design two, the only difference is the viscosity for this one. So the friction power and total power reduce significantly. And this is the temperature rise for the parameter. Then you can change the viscosity to this one. So these three, the first three designs, the only difference is viscosity. So and then number four, compared to number one, the difference is the clearance, the bearing film gap thickness. Okay. So this we increase the film thickness from 13 micron to 32 micron. So the thickness dropped significantly. So this one is 180. Here is only 73. So when you need to change the clearance, it's very critical. So we need to examine the performance very carefully, especially for the stiffness. So you increase the clearance, then the friction power drop from 4.38 to 3.46. So the friction power is dropped, and then the total power is dropping. So the temperature rise will drop from 37 to 1. Okay. And for the fifth design, the only change is the language ratio. So we reduce the language ratio. So the stiffness is not affected, okay, but the total power is dropping because the friction power dropped significantly. So the temperature rise will drop as well. So you can, when you read the text for the design parameter, you can look at the numerical example for this table 3.1. You can see the effect for that. So normally we will not change the clearance. The film gap thickness is very critical to the bearing performance. You can change the other parameters clearance. Yeah. So this probably is true for the low speed bearing. So for the power ratio ranging from 1 to 3, almost the same. Yeah. But for the power ratio greater than 3, which means it's a really high speed bearing, you should also take care of the some design parameters. For instance, the total power of the bearing. So only, I would say only 10% of the machine tool applications, they are fully to this capable. Most of the case I'm facing for the machine tool industry, only I think I never encountered this problem. They don't have any application in the high speed isostatic bearing. So you always design the hydrostatic bearing using the low speed bearing strategy. Okay. 所以大部分来讲，唯一目前可以看到的就是钻孔机，50万转的钻孔机或30万转以上的那个电路板的钻孔机，才需要去考虑高速走程的问题，其他的基本上完全不需要，都是用低速走程，甚至是用速度为零来设计都没有问题。可以，for the reference, I will show you the reference. So this is the reference for the chapter 3. So most of the result was published from 60 and 70, I think, or 80. So for the theoretical study of hydrostatic bearing, somewhere almost done everything in 1980. So most of the textbook for hydrostatic bearing design starting from dated from the 1983, I think. Yeah. 所以大部分的其实理论研究的部分，在静压轴承来讲，大概都是60年代、70年代其实都已经做完了哦。所以教科书的话，像我们这一本书的作者，他其实前面写了一本，就是1983年写的静压轴承的设计。那也是大概就是1987年。其实1987年很多教科书，你如果去查一下， hydrostatic bearing. If you check out the catalog in the library, you will find out a lot of textbooks for hydrostatic bearing were published in 1980s. 大部分都是1980年就已经写。那其实是因为最近啊，就是其实大概是2000年以后，高速切削这些高速运用还有超精密加工的需求，所以静压轴承才又被人家重视哦，就是超精密加工机一些工具机就是往超精密这方面走，所以静压轴承就被拿出来用。So lots of development at the 2000 year 2000 because of the precision engineering and precision machine tool. So the hydrostatic bearing design or aerostatic bearing design was regain the focus from the researcher or machine tool manufacturer. So we get the attention from that. 所以大概2000年以后才会又有一些大部分都是工具机的厂商，他们又重新重视这个静压轴承设计。像我们台湾的一些磨床的厂商，他们要走比较高端的机台，是要走超精密、超精密加工机，磨床、铣床、车床，那么都需要静压轴承、静压主轴、静压工作台。So in here, in chapter 4, we mainly discuss the bearing pad area, how we can calculate the pad area. Because for us, the mechanical property of the hydrostatic bearing, especially for the low carrying capacity, nothing. We are interested in this one. And for this one, in chapter 3, we tell you how to calculate or estimate the research ratio for different restrictor. Or this is restrictor or capillary restrictor. How can you calculate the PR? In this chapter, we are going to tell you how you can calculate the bearing pad area. So this one, pad area. So In this case, then you can, using this formula, the PR multiplied by the equivalent bearing pad area, you can have a low capacity for your bearing, for your hydrostatic bearing. For instance, you have a 4 bearing pads. Each bearing pad area you can calculate, and then you have a recess ratio, and you can multiply the number to 4, and then you have the total load capacity. For example, the slide table, you have a 4 pad, and then you know the load capacity for this hydrostatic bearing. What is the maximum load capacity for this one? So in this chapter, you may know how you can calculate or estimate the bearing pad. As we know before, in fluid mechanics, we usually using the non-dimensional notation for the for your fluid performance. So here we have a non-dimensional parameter E. Okay. So the key formula for this one is load capacity equal to PR multiplied by equivalent pad area. And also, we are going to tell you how we can estimate the volume flow rate for each bearing. Okay. And similarly, for the aerostatic bearing, you will have a formula for that. And then here we have a non-dimensional notation here, A bar, B bar. Okay, we will explain later in this chapter. Okay. Yeah. So the load capacity W equal to the PR multiplied by A and A bar. So this notation A multiplied by A bar equal to the equivalent pad area or so-called effective pad area A. And we also introduced another new parameter here. It's called the flow shape vector V bar. So this flow will depend on the flow shape vector V bar. Angular shape vector V bar and flow shape vector V bar. It's just a notation. And first, we come back again for the virtual reset. Yeah. When we explain for the flow theory in chapter 2, we mentioned about the virtual reset. Okay. So virtual reset is meant for the A bearing. So this is the normal hydrostatic bearing. You have a reset, square reset here. The inlet hole or oil supply hole is in the center. Okay. So this is the pressure distribution for your bearing height. Okay? And from the edge is equal to the end velocity relative to zero. And here in the center, inside the recess, the pressure for the recess is called the PR. So have this measure on this unit. For air bearing, due to the symmetrical instability, so we tend to design the air bearing without recess. But we try to increase the stiffness or increase the recess pressure during the pad area or inside the pad area. Another alternative way is using the virtual recess. We can instead of drilling only one hole in the center, you can drill 8 holes. Okay? And this line like a square line inside the test area. So in each inlet hole, you have a reset pressure. Reset pressure. So in that case, you will have increase your reset pressure inside the bearing head. But I told you that you have another problem because each inlet hole you need to connect the oil pipe. You need to connect the restrictor. Actually, it's very difficult for the installation of those oil line and also restrictor. So this is a theoretical capability. In theory, you can do this, but in practical, nobody do this because it's a disaster when you come to the connection of the oil pipe and restrictor behind. Because for your machine tool, you have multiple recess. So, and then for each bearing that you need to have 8 connection of the oil pipe and restrictor. For multiple ones, you have a lot of more for the oil pipe connection and restrictor connection. So it's really not practical to do this. Okay? But in this case, you can have some, this is some theoretical study called the run factor. Okay? Describe the extent at which entry source surrounded by a virtual reset. Okay? So in this case, you can analyze the performance of the virtual reset. There are some studies on this, and there are some results as well. So we can look at the figure in 4.2, 4.2 and 4.3. This is the comparison for the design chart. This is a bit too small. comparison table for that. This is the design chart for the circular bearing that have reset in the center. So the bearing head is a circular one. So the, the language is equal to A. Okay. The diameter is B. This is for the I mean the hydrostatic bearing. So, to have the similar performance to do so, for the air bearing, you can use the virtual reset design like this. Okay. The similar from the interval to the edge of the circular bearing head. The distance is A equal to the length. And this is the data for the circular bearing head design. So with the language ratio, A divided by D equal to 0.25, we have this chart. Okay. So we have an area shape factor and flow shape flow shape factor V bar. Okay. And for this one, we can calculate the non-dimensional pumping power. Okay, and then for different supply pressure, you have a different curve for that. This one is hydrostatic bearing, and these two are the air bearing. So for air bearing, you have only two recessed pressures because for the air bearing, as I mentioned before, usually the supply supply pressure was not greater than 6. So the reset pressure like this is already overestimated. Okay. So this is for the circular bearing with virtual reset. This was a drawing, was a figure in page 67 for the circular bearing head. And we have another drawing for the rectangular bearing head. So by doing so, we have virtual reset, which has a similar effect like real reset. So this is the chart, design chart of the A bar and B bar. And this is for the pumping power. Okay. For the language ratio is equal to 0.25. So because this is optimum design parameter, so we always choose this one. Language ratio is equal to 0.25. So in 1980s or 1970s, the engineer, they want to design the hydrostatic bearing, they always using this chart to do so. So at that time, the tribology or bearing handbook, they are always using this design chart for the design of a hydrostatic bearing or aerostatic bearing。是早期基本上都是用这个图表来做设计，你就是查你的表，你的 first check on your the selection of your language ratio, and then you can have a B bar, B, A bar for that. The next one, we look at the rectangular one. Okay. This is another example for the design chart for the rectangular region hydrostatic bearing. Okay. So again, in this, in the right hand side is the virtually set design. So for this, they have a different choice of the parameter. The language ratio equals to 0.25, and the for the rectangular shape, the width or length divided by width between 1 and 2, you can use in this chart. So you can check on this for the A bar and B bar. Aerial, aerial factor and aerial shape factor and flow shape factor for the A bar and B bar. And for your textbook, each chart will follow an example how you can use this chart to do the design of this bearing. Okay. Here is a section 4.3. We are introducing the formula for the circular bearing head. Okay. So this is the formula of how we can derive the area shape vector B bar, and also the flow shape vector B bar in this case. So earlier in chapter 2 or chapter 3, we discussed about this one, the low capacity for the central speed circular bearing. You have the low capacity using this formula. You can estimate the exact low capacity for the bearing. And in this chapter, we introduce you, we are using the non-dimensional parameter, using the area shape vector, how you can do the estimation. Okay. Actually, the similar, the same result, but different notation. 其实我们前面第二章已经介绍过这个理论的部分，这个是承载力，这个是流量。那只是我们这一章是用别的代号来表示，就是我们用形状、面积形状系、形状的因子或者跟流量形状因子 A 坝跟 B 坝来 做不同的表示。这个只是推导。This is the relation how you can obtain the area shape vector A bar and flow shape vector B bar from the formula. And in this case, the flow capacity W and volume flow rate Q can all using this new notation, A and A bar or B bar. So this was in the page 70 in your textbook. Similarly, you can have your pumping power using these notations, all from the flow, flow shape vector and area shape vector. So by using this, we are try to solve the optimization problem for maximum load for minimum power for circular bearing. You can nearly obtain the language ratio equal to 0.24 is the optimum value. So it's not far from our rule of thumb, 0.25. OK，这其实是从理论推导，就是有个最小功率消耗最大的承载力。我们其实可以找到，如果是圆形平面轴承的话，它的最佳的那个风油边宽度比，风油边跟它的宽度比大概是0.25，其实已经非常接近我们的0.25，所以我们其实都用0.25，为什么？我们前面在讲，如果你设计轴承的话，都是用0.25。So this is why we always design our language ratio using the 0.25. It is because the optimum value for the maximum load or minimum power for circular bearing is equal to 0.24. It's very close to 0.25. 0.25这是1/4，比较好记，所以都用这个。OK，这只是原则啊，风油边宽度，风油边跟宽度的比值0.25是原则。那你如果发现它的温升太高，你就把风油边降低，你就可能不是0.25，降为0.2。当然，你风油边的宽度减少，你的流量就会增加。那你有发现你的轴承的总流量太大，那我就把那个风油边宽度加大。风油边的宽度加大，就表示那个油膜间隙很窄的地方的宽度变得很宽，所以我的油流出来就会流得很慢，所以我的流量就会很小，就可以降低流量。所以这个是你可以去操作，就是你可以依照实际的状况去增加或减少。 4.3 using the this equal to 0.25.那这个是here is a square bearing height. Okay. So we are also using the same language ratio equal to 0.25. We have also example for this one. To the rectangular bearing height as well, you are using the similar choice of the language ratio equal to 0.25。就是葱油边跟宽度的比就是1:4。其实对那个头颈轴承也是一样。For journal bearing the same, the language ratio equal to 0.25。Let's take a break here. Okay. There is another uh, truss bearing shape. It's called the annular circular bearing. So the recess is here. Okay. So this is annular bearing. The recess is in the center. There are two inlet holes here. For here, we have multiple inlet holes. You have a 12 inlet holes. You have only one recess, is annular recess. 哦，这个是通常是主轴的指挥中心。This is the truss bearing for the spindle. So here is the recess. Only one recess. There are different designs for this. You can have a multiple recess. But here you have only one recess with a 360 degrees. In page 16, page 16, I'll try to remind you. Yeah, for example, for this is also a circular, annular circular bearing, but here we have 8 recess. Instead of one, you have 8 recess in the circle. But for our example here, we have only one recess. The design for this one is better than one reset because if you have multiple resets, you tend to have a better resistance to the tilt moment。所以其实是多重油枪会比单一油枪好，是因为单一油枪的话比较不利于倾注力，多重油枪会比较好。So this is another design chart for the angular circular bearing, annular reset circular bearing. Okay. And then for the next section is for the journal bearing. We have a conical journal bearing. Wait. This is the conical journal bearing. Remember, we have already introduced this. One. Try to get a small one. Okay. So this is a conical journal bearing. So for the left hand side is the reset conical journal bearing. And for the right hand side is the plain conical journal bearing. So without any reset. So particularly for the air bearing, we prefer this kind of design without reset to avoid the numerical instability. 所以对气压轴承来讲，大部分他们都希望是没有油墙的设计，这样子就不会有气水的发生，气水不稳定现象。So this bearing can be used in the spindle, the conical John bearing spindle in this case. And the other one is the spherical bearing. Okay. The same. This one is the left hand side is with the reset design, and this one is without reset. Okay. So this is the semi spherical spherical bearing. Okay. So we have this design chart. So the notation is again is wrong. So this A might be the alpha, okay? The Y might be the gamma. So the notation is incorrect in this case. This one is alpha, this is gamma. Again, we have another form of the bearing called it multi-recessed circular pad. So this kind of bearing is multi-recessed circular bearing pad, especially with the ball bearing here, 360 degrees. And we have the A bar area shape factor and also B bar flow shape factor, B bar for the design. So we have a design chart for the language is divided by the R, the radius between point 15 to point 25. And here another one is called the multi-recessed rectangular pad. So the level is in the right hand side, left hand side, and right hand side. In between is 2A. So there's also A bar and B bar with a different length divided by width ratio between 1 and 2. And the length width ratio is equal to the point 125. It's very small or very thin language. Okay. So for the classical hydrostatic bearing design book, you can see a lot of the design chart like this. So you can design your bearing according to the shape of the bearing you want to design. And this is another case. In before, we always discuss the recesses, rectangular shape. So the corner is 90 degrees for the recess. In this case, you have the corner, you have a radius, small radius R here. There is a slightly different for the result, but uh, I once saw a published paper discussing about this effect uh, for the wrong corner of the research. So that effect is you will get a smaller low capacity compared to this kind of a rectangular corner. Okay, but the difference is very small, less than 2%.所以这个直角的跟圆形的角的油枪其实差异差不多，2%，2%其实制造公差大概是5到10%，就是我们一般尺寸的公差影响到你最后的系统大概是5到10%，所以它2%其实是等于没有影响。So this is the design chart for this rectangular and rigid reset corner in this case. And another one is a very special case. Is for any shape with C constant length width. So that means the length width is very small for the hydrostatic bearing. In this case, the friction power is less, but the volume flow rate will be uh, getting a lot of more compared to regular language ratio. Okay? But this can decrease the temperature rise for your lubricant. This is so-called the thin language bearing, hydrostatic bearing. So in this case, we have a formula for the A bar and B bar. Okay. So this is for the rectangular bearing pad. Okay. And we also have an annular multi-recess bearing pad like this. Okay. So here we have 6 pads in this 350 degrees. We have 6 pads. And for air bearing, we tend to use without any reset. Instead, if you still want to increase your stiffness or low capacity, there's another way. You just have a small groove, okay? Very small groove. So why is it called? 你可以挖沟槽，不是油墙，是挖沟槽。The width of the recess almost the same as the inlet hole diameter. 就是那个油箱的宽度大概就是跟我们的路由管的直径差不多。很多时候我们看到的就是挖沟槽。 就是挖一个大概几米米的一个沟槽，大概3到5米左右的沟槽。So here we have some suggestions for the design range. Okay, this one is for the multi-pixel angular circular bearing pair. Okay, the net width ratio lying between point 0.1 to point 0.3. Here is the net width ratio lying between equal to the point 0.5. This is some suggestions for you if you want to design a bearing like this. So before you always using this design chart to do your design. So for the classical textbook, you always see this kind of design chart. But nowadays, usually you use finite element software. Finite element. So now we can construct a model for the hydrostatic bearing in ANSYS module fluent. Actually, Fluent is one individual software company, but finally it was obtained by the ANSYS software company. So, so Fluent become one of the modules in ANSYS that can analyze the software and then analyze the performance of hydrostatic bearing and aerostatic bearing. Okay. Of course, in America, there are also several software companies that develop some special software to analyze the hydrostatic bearing and aerostatic bearing. Okay. But it's not so famous like ANSYS. 就是现在的话，大概都是用 ANSYS 的图文这个模组来做分析。但是以前的话，Fluent 是一个独立的软体公司，它只是被 ANSYS 买走，现在变成它底下的一个模组。So in America, you can also buy a software called R. It's also a software you can use to analyzing the hydrostatic bearing and aerostatic bearing. Okay. This is a special software developed by one of the American companies, but it's not so popular like ANSYS Fluent. Okay. Is there any question about the this chapter? There is that for the area shape factor A bar and flow shape factor B bar. This is a classical way to design the hydrogen bearing. So depending on what kind of bearing type you are going to design, you can using this chart. Of course, for different language ratio, you should choose a different chart. Okay?是早期基本上都是在70年代、80年代电脑不发达的时候，都是用图表来做设计。But nowadays you need to construct the finite model in Fluent to construct your bearing parameter, okay, and then you can analyze the performance like the recess pressure and the bearing at the area and also the load capacity. And if you give the film thickness to your model, then you can analyze the thickness. Okay. For the virtual recess, you just forget about it. Okay? It's just a concept. It's no use in practical product design. Any questions for today's lecture? The midterm exam will be organized just after we complete the lecture on chapter 5. So maybe, I think maybe 2 weeks later. Yeah. Okay. It's open book, but so that's why I suggest you to bring out the textbook. Okay. So the question, okay, so the exam will cover from the chapter 1 to chapter 5. And next week we will continue to give a lecture. Okay. Probably after next week we can set a date for the midterm exam. 就是期中考的部分，第5章讲完了以后才会考，就是会 open book 的考试，所以你还是要去看一看。所以我才会建议你，就是把书印一印，就是上课的时候有讲的话，不会中文的时候可以把它写上去。Okay. Any questions for today's lecture? Okay, then see you next week. Thank you.